Hi, this is Physics 221, Mathematical Physics 1, and this is the second part of our lesson on matrices and vector spaces. In part 1 of this lesson, we ended up our discussion with the Hermitian conjugate of a matrix. The Hermitian conjugate, or the adjoint, again, is denoted by your A dagger, which is just a transpose of its complex conjugate, or equivalently, the complex conjugate of its transpose. That is, the Hermitian conjugate A dagger is equal to the transpose of your complex conjugate, or the complex conjugate of its transpose. And we note that if A is real, then your A dagger is equal to your A transpose. The Hermitian conjugate of a product can be shown to be given by this following expression here. Important use of the Hermitian conjugate, or the transpose in the real case, is in the connection with the inner product of two vectors. Suppose that in a given orthonormal basis, the vectors A and B may be represented by the column matrices A here in the column matrix B. So we have written your vector A in terms of the column matrix with A components, and your vector B in terms of the column matrix B with your B components. And by the way, we can also write this one in this way. So we can say that you have your ket A, or we can associate your ket A with your column matrix. So you have your A1, A2, up to AN. And also, we can represent your, or associate your vector B with ket B with still the same column matrix, B1, B2, up to Bn. Okay? And if, say, for example, you have Z, which is a complex number. So Z is a complex number, and we have your Z ket A. Remember that Z is a complex number, and this A's here and this B's here are actually also complex numbers. So remember this one. Your A components and then your B components are also complex number. And again, if we have your Z, which is a complex number, and we multiply Z with your ket A, then it is actually not true. So it's not true that your Z ket A is equal to your bra A times Z. Because remember that your A's, your B's, and then your Z's are complex numbers. So therefore, since they are complex numbers, then you have to get the complex conjugate. So you have to get the complex conjugate. Okay, so that means your the corresponding bra to your, so let me write here, the corresponding bra to your Z ket A is your bra A Z star. That is the complex conjugate. But you also need to get the complex conjugate of your A components. Okay, so again, if we have your ket A represented by the column matrix, then your bra A, so let me erase some items here. Just let me erase this one. Okay, so if this is your ket A here, then the corresponding bra, which is your bra A, is the column matrix A1 star, A2 star, that up to AN star. That is, we got the complex conjugate of your A components. So your ket is a column matrix, and your bra is a row matrix. In the previous slide, we've shown that, or we've stated that your ket A can be represented by the column matrix A, and then your ket B, or sorry, your bra A is the is represented by the, what do you call this, the row matrix. But in order to get the corresponding bra to your A, to your ket A, we we took the Hermitian conjugate of your vector A. That is, we took the transpose and then we took the complex conjugate. Or you can also do it in the other way, wherein you take the complex conjugate of your vector A and then you get the transpose of your A. So here, taking again the Hermitian conjugate of A to give a row matrix. So you have this one now here, okay, and multiplying it with your B. So that is your A dagger times B. That's equal to this Hermitian conjugate of A times your column matrix of B. So this is just actually, if you're going to multiply this one, you see that this is just equal to the sum of your AI star BI, which is, as you can see, this one here is just the expression for the inner product, which is your bra A ket B in dot basis. And if we have real vectors, this one just reduces to the following here. Is just the sum of your AI BI, but here your A is equal to the transpose, or your A is the transpose of the previous vector A times your B. So here again, this is still your row matrix, and then this is your column matrix. Now let's discuss the trace of a matrix. And as you can see, sometimes one wishes to derive just a single number from the matrix. And one of the simplest single number, for example, is called the trace or the spur of a square matrix, which is denoted by your trace A here. So your trace A is only valid for your square matrices. And this quantity is defined as the sum of the diagonal elements of a matrix. Again, your trace or your spur is defined as the sum of the diagonal elements of a matrix. So whatever you have, uh, whatever square matrix you have, let's say for example, you have your A11, A12, A13, A21, A22, and A23, and you have A31, A32, A33. Okay. If you want to get the trace of this one, we just get the sum of the diagonal elements, which is this one here. Okay. And taking the trace is a linear operation, so that, for example, the trace of A plus B, or the trace of A minus B, is equal to the trace of A plus the trace of B. The trace of the product of two matrices is independent of the order of their multiplication. That is, if you want to find for the trace of A times B, which is equal to the sum of your matrix A times B, okay, which is you have your I that's equal to J, so you have here your II. Then just remember that you can rewrite this one in this term here, and if we interchange your A times B like this one here, as you can see, this can be written as your B times A JJ. So we have your J that's equal to 1, or your J that's equal to I, so we can just write it as just one sum. You have just your J, the sum of your B times A, JJ. And as you can see here, this is just actually the same with your trace times B, trace of B times A. So it's independent. The trace the trace of the product is independent. So whether you have trace of A times B, that's equal to the trace of B times A. And this result can be extended to the product of several matrices. If you have three matrices and then you want to get the trace of the product of your three matrices, so if you have the trace of B of A, ABC, it is equal to the trace of BCA, or it is also equal to the trace of CAB. Other easily derived properties of the trace are the following. So you have the trace of A transpose is equal to the trace of A, and the trace of your A dagger, or the Hermitian conjugate of your A, is equal to the trace of or the complex conjugate of your trace of A. Okay, so these are some of the easily derived properties of your trace. So now let's discuss the determinant of a matrix. Okay, for a given matrix A, the determinant shown as your det A, like the trace, is a single number or just an algebraic expression that depends upon the elements of A. And also, like the trace, the determinant is defined only for square matrices. So you cannot get the determinant or the trace of your matrix if they are not square matrices. So when we say square matrices, the number of rows are equal to the number of the columns. Okay, so you have the determinant of A, which can also be written as your uh, your absolute value of your A, or you have this absolute value symbol. So when you see this one, what we actually mean is the trace, or sorry, the determinant of your matrix A. So if these are the components of your matrix A, okay, in order to calculate the value of the determinant, we first need to introduce the notions of the minor and the cofactor of an element of a matrix. So again, in order to find the determinant of your matrix, we need first to discuss about the minor and your cofactor. So the minor, which we can write as your Mij, so your minor Mij of the element Aij, so referring to any element of your matrix Aij of an n by n matrix. So when we say n by n, what we mean is your square matrix. Okay. So again, the minor Mij of the element Aij of an n by n matrix A is the determinant of the n minus 1 times n minus 1 matrix obtained by removing all the elements of the ith row and the jth column. So again, the minor Mij of the element Aij of an n by n matrix A is the determinant of the n minus 1 times n minus 1 matrix obtained. So when we say n minus 1 times n minus 1, this is obtained by removing all the elements of the ith row and the jth column. So see, for example, you have your matrix A. So this is how you write your matrix A. You have your A11, A12, A13. You have your A21, A22, and A23. Then we have your A31, A32, and A33. So you can select any element of your matrix, any element Aij. Now let's say, for example, I like to get this one, your A13. So let's suppose that your A13 or our element, sorry, let's suppose that your element Aij is your element 1 to your element 1, 3. That is your I is equal to 1, and then your j is equal to 3. And to get the minor of your A13, okay, we remove all the elements of the ith row and the ith column. So we remove the elements of the ith row. So that's the ith row. So that's the first row. So what we are going to do is we are going to remove this one. So let's just cross this out. Okay, so let's cross this one. And let's also cross this one, because you're going to remove all the elements of the ith row or the first row. And next we're going to remove all the elements of the jth column, that is the third column. So we remove this one and we remove this one. So we have this one here, we are just left with with 4 elements. Okay, because as you can see, or we already have your n minus 1 times your n minus 1. So initially we have a 3 by 3 matrix. Now we only have a 2 by 2 matrix, so you have 4 elements. And the minor Mij of the element Aij of your 2 by 2 matrix is just the determinant of this matrix. So how are you going to get the determinant of this matrix? What you need to do is just to multiply these two. So the determinant now of your let's just take this one. You have your We now just have this matrix here. Let me choose a different color. We now just have your matrix A21, A31, A22, and A32. And the determinant of this one, okay, the determinant of your sorry, let me just erase this one. So the determinant of this one is equal to your A21 times A32 minus your A22 A31. So we just have an advanced determinant for your 2 by 2 matrix because it's just easy. Okay, but if you go to higher levels or higher number of your matrices, getting the determinant would be a little more harder. So the minor MIJ of the element Ij is the determinant of your n minus 1 times n minus 1 matrix obtained by removing all the elements of the ith row and the ith column. So this one here, this determinant here, this is actually equal to your M13. So this is the minor of your A13 element. So the minor of A13. Okay, so again, what we just did is we select any random element of your square matrix, or your 3 by 3 square matrix. And for this case here, we took your A13 such that you have your I is equal to 1 and then your J is equal to 3. Okay, and we remove all the elements of the first row and we remove all the elements of the third column. So just as you can see here, we cross out your first row and then your third column. And after that, we get the determinant of your 2 by 2 matrix, which is just your A21 times A32. So we multiplied your A21 to A32 minus the product of A22 times A31. And this determinant here is equal to the minor of your 1, 2, 3. That is, this one here is your Mi3, the minor of your A13. And the associated cofactor, which is your Cij, is found by multiplying the minor by -1 raised to the I plus j. So for this case here, since your I is equal to 1 and then your j is equal to 3, your cofactor of 1, 3 is equal to -1, sorry, it's equal to -1 raised to 1 plus 3, or that's 4. So you have -1 raised to 4, that's equal to 1. So that is the cofactor of your Aij, or your A13 element of your 3 by 3 matrix. So the cofactor is just easy since it's just your -1 raised to your I plus j. Okay, so we now have defined your minor and then your cofactor, and we're now ready to define we're now ready to get the determinant of your 3 by 3 matrix. So this is another example. Find the cofactor of the element A23 of the matrix A. So we have the same matrix A as before, and we are asked to find for the cofactor of your element A23. So where's your A23? So this one here, this is your A23. And we need to find the cofactor. But of course, before we can get the cofactor, we first need to find your minor, 2, 3. And then after taking the minor, we can now get the cofactor of your 2, 3. Okay, so here your I is equal to 2, and then your J is equal to 3. Okay, so what we do is we remove all the elements of your second row and all the elements of your second column. Okay, So just remove your second row elements. Let's just erase this one, also this one, and your third column elements. Okay. So what we are now left is just a 2 by 2 matrix with elements A11, A12, A31, and A32. So removing all the elements of their second row and the third column A and forming the determinant, the remaining gives this one here. So as you can see, when we are talking about the determinant, instead of this, how do you call this symbol here, you now have this absolute value representation, meaning we are going to take the determinant of this one here. And earlier, I've shown you how to get the determinant, but it was just actually a shortcut. Okay, so that is your this is your M23 determinant of this one here. So you can now get the cofactor of this one. So multiplying the minor by your negative 1 ratio to 2, 3. So again, your cofactor 2, 3 is just your negative 1 times your I plus j. So that's equal to negative 1, 2 plus 3, which is 5. So you have negative 1. So earlier you have your minor 2, 3, which is equal to A11, A31, A12, and A32. So multiplying with your the minor by this value here, which is equal to negative 1, we get your cofactor 2, 3, which is equal to the negative of the determinant of your minor 2, 3. Now let's have a proper definition of your determinant. When we say the determinant, this is the sum of the products of the elements of any row or any column and their corresponding cofactors. So again, your determinant is the sum of the products of any elements of any row or the elements of any row or any column and their corresponding cofactors. What we mean by this one is that if you have your matrix A, which is equal to A11, A12, A13, A21, A22, A23, and then A31, A32, and A33. Okay, when we say the determinant, it is the sum of the products of the elements of any row or column and their corresponding cofactors. So to get the determinant, you can choose any row or any column. Like say, for example, I can have this one, or I can have this one, or I can have this one here. So I just select any column or any row, and then I will get the cofactor of the elements, of the corresponding elements. Like say, for example, I choose the second row. So for the second row, so this is for the second row. Take note that the elements of the second row are your A21, A22, and A23. So for this case here, in order to find for the determinant, we just randomly selected your second row. And to get the determinant is the sum of the products of the elements of your second row and their corresponding cofactor. So you have your second row A21 element times the cofactor plus your A22 C22 plus A23 C23. We can also get the determinant by using your, let's say, your third row or your third column. Your third column. So the elements of your third column are A13, A23, and A33. So we multiply the elements by their corresponding cofactors, and then we get the sum. So you have your A13, C13 plus A23 plus C23 plus A33, C33. And this sum here, such a sum is called your Laplace expansion. So you call this one here as your Laplace expansion. Again, to get for the determinant, you have the freedom, let me specifically write here, you have the freedom to choose any column or any row. Okay, so but just remember that the determinant is the sum of the products of the elements of any row or column to choose and their corresponding cofactors. So let's have an example in finding for the determinant. Okay. Example using the elements of the second row of the determinant defined by your determinant A. Okay. So we now have this one here. Okay, so remember here that if you have these two parallel lines, your absolute value symbol, what we are referring to is your determinant. If you have your parentheses, that means it's just your matrix. Okay, so if you see this one is for your matrix. If you see this one, this is for your determinant. Okay, so just to remind us of our symbols. Okay, so example using the elements of the second row. So we're going to find the determinant by choosing your second row. So if we are again choosing your second row, this one here, you're going to multiply the elements with the corresponding cofactors. That is your A21 times C21 plus your A22 C22 plus A23 C23. Okay, so you have your okay. Uh, Let's have first your A21. So your A21, so any value of your A21 times the cofactor of A21. So just an example for your the minor of your 21 and then your cofactor of your 21. So we remove all the elements of the second row and we remove all the elements of the first column. Okay, and your C21 is equal to -1 raised to the power of 2 plus 1. So that's 3 here. So you still have your -1. So this is we're just left with A12, A13, and then A32, and then A33. So that is your minor. So we need to get the determinant of these elements to get the minor to 1. So as you can see, this is this one here. So you have your times -1. So your A21 times C21 is negative A21 times the determinant of A12, A13, A32, and A33. And you do it with the next elements, okay? So again, for example, you have for your A22. So for your A22, we remove all the elements of the second row and the second column. So we're just left with A11, A13, A31, A33, which is this one here. As your cofactor, which is 2 plus 2, which is the cofactor of your C22 is -1 times 4, so that's positive. So you have plus A22 times the determinant of these elements here. And lastly, we do it for your A23. So for your A23, we remove all the elements of the second row and then the third column. So we're left with A11, A12, A31, and A32. And the cofactor is -1, so we just multiply it with -1, this one here, and take out the negative expression. So you have this one here, this expression here. This is the determinant of your 3 by 3 matrix. And we will see later that the value of the determinant is independent of the row or column chosen. So whether you get or so just say for example here, we choose we chose the second row. But we can also get the same expression whether we get your third column or your first row. So we'll see later that the value of the determinant is independent of the row or your column that is chosen. Earlier, I have shown you how to find the determinant of a 2 by 2 matrix. But that was actually just a shortcut on how to find for the determinant. And if you're going to use the definition of of your your minors and cofactors to find for the determinant, finding the determinant of a 2 by 2 matrix goes like this. But before that, let me call, or let's say that your matrix A is equal to your uh, your A11, A12, sorry, your A11, A12, A21, and A22. Okay, and let's say that your A11 is equal to A12, your element A12 is equal to A13, and your element A21 is equal to A32, and then your element A22 is equal to A33. Okay, so what you see here, these are not actually what your element is. So these are already actual values of your elements: small a11, small a12, small a21, and then small element a22. Okay, because this might actually confuse you. So that means this one here is your first row. This one here is your second row. This one here is your first column. And then this one here is your second column. Okay, so I hope that is clear. So let's find for the determinant of this matrix here. So let's find the determinant of this one here. And again, to find for the determinant, I can choose any row or any column. And let's say just for this example, I choose to find the determinant using your first row. So using the first row, that means I have A12 times your C11, because again, your A12 is your small A11 element, okay, plus your A13 times your C12, okay. So now let's find for the cofactors. But to find the cofactor, we need to first find the minor, okay. What's the minor of this first element here? The minor of your A11, okay, is or can be taken by finding, okay, let me write it here. I'm looking at your element A11, so I'm looking for the minor of M11. So we remove the first rows and then the first column, so we're just left with A33. So this is just one, so this is already the determinant. And the cofactor, therefore, is your um, A33 times negative 1, 1 raised to 1 plus 1. So this is 1 plus 1, that's positive. So you have your C11 is equal to A33. So that is this one here. So you have your A12 times the cofactor. Okay, so that is A12 times A33. Okay, again, that is A12 times A33. Next, I have for your small a, again, small a12. For your small a12, that is, I'm looking now at small a12, meaning I'm looking at this one here. So to find the minor of 1, 2, that is, we remove the first row elements and then the second row elements. So the minor is equal to A32. And the cofactor of 1, 2 is just your A32 times negative 1 raised to, um, that's raised to 1 plus 2. So that's negative. So you have here your your A13, as you can see here. So you have your A13 times the cofactor of C12 because your A13, your big A13 is your element A12. So we need to find the cofactor of 1, 2, which is this one here. And the cofactor is equal to negative A32. So multiplying your um, A13 with negative A32, so you have negative A13 times A32. So you have now, evaluating this one here, you have A12A3 minus A1332. That is finding the determinant using the definitions of your cofactors and your minors. But to show you that the shortcut is just correct, so you have A12 times A33 minus your A13 times A32. So we get the same answer. So we are now ready to find for the determinant of your 3 by 3 A matrix. And in the previous slides, we had this one, okay? You remember we had this one, and we have this one from the second row. So what we did was to find for the determinant using the second row, and we are left with this one here. Okay, so this is your A21, the cofactor of A21, A22, the cofactor of A22, and then A23, the cofactor of A23. And you already know how to find for the determinant of your 2 by 2 matrix. That is, for this case here, you have, for the first cofactor of your 2, 1, so that's A12 minus, or A12 times A33 minus A13 times A32 plus A22 times this one here, A11 times A33 minus A13 times A32 minus, so this is this one here and also this one here, minus A23 times A11 times A32 minus A12 times A31. So you have this one here. And rearranging, we get the determinant of A, which is equal to A11 times A22 A33 minus A23 A32 plus A12 A23 A31 minus A21 A33 plus A31 times A21 A32 minus A22 A31. So this one here is the determinant of your matrix A. And take note that you can also get the same expression if you use your third column or your first column or your first row. And I will be leaving it to you to show that indeed, even if I choose your third column or your first row, I can get the same answer here. Now suppose you have the rows of a real 3 by 3 matrix A, which are interpreted as the components in a given basis of 3 vectors A, B, and C. Show that one can write the determinant of A as your A dot B cross C. So we're going to show that we can actually find for the determinant of A using your A dot B cross C. And if one writes the rows of A as the components in a given basis of 3 vectors A, B, and C, let's write your determinant A as the basis of 3 vectors A, B, and C, that is A11, A12, A13, B1, B2, B3, C1, C2, C3. Let's have this one here. And you already know how to find for the determinant of this one. And let's say that for this specific case, let's find the determinant using the first row. Okay, so you have your A1 times your C11, your A2 times C12, and then your A3 times C13, which is equal to this term here. And as you can see, if you can remember, from the expression for the scalar triple product. This is for your scalar triple product, which is just equivalent to this one here. That means we can find for the determinant of your 3 by 3 matrix using your A dot B cross C. So it's true. So the determinant of your 3 by 3 matrix is equal to your A dot B cross C. Let's have some flashback. Do you remember your cross product of your two vectors, A cross B? We have actually written this one to find for the cross products in a matrix, a 3 by 3 matrix for your real vector, your real vectors A and B. So what we did was on the first row you have your I hat, your j hat, and then your k hat. And for your second row you have your ax, ay, and az components, and then your bx, by, and bz components on your third row. Okay, and in order to solve for this one, we did some techniques. And what we actually was doing with the cross product using this matrix here is that we find for the determinant of your matrix. So we got the determinant by using your first row, okay, and the rest is history. So you can verify it that what we did was to find for the cofactors. So let's say for example, for this case here, you have I hat times the cofactor C11 plus j hat times the cofactor C12 plus k hat times the cofactor C13. And just for example, for your C11, we remove your first rows and then your first columns. Okay, so you have your I hat times your ay bz minus az by. Okay, so you can follow through the next steps. So what we actually did in our previous discussions with your cross product was use the determinant to find for the cross product of your two real vectors, A and B. Here are some properties of your determinants. So you have the determinant of the transpose. So the transpose matrix AT has the same determinant of A itself. So that is the determinant of your A transpose is just equal to the determinant of A. Next, we have the determinant of a complex and Hermitian conjugate. It is clear that the matrix A star obtained by taking the complex conjugate of each element of A has the uh, determinant of A star, or your determinant of A and then star. Combining this result with the first one here, the first property, we have the Hermitian, the determinant of the Hermitian conjugate, which is equal to this one here, okay, which is just equal to your the determinant of your A star or your determinant of A star. The next property is interchanging two rows or two columns. If two rows or columns of A are interchanged, its determinant changes sign but is unaltered in magnitude. So again, if you have any two rows or any two columns that you want to interchange, the magnitude of the determinant is unaltered, but the sign of your determinant is changed. And then you have your removing factors. If all the elements of a single row column or column of A have a common factor lambda, then this factor may be removed and the value of the determinant is given by the product of the remaining determinant and lambda. So let's say for example, again, for your removing factors, if all the elements of a single row or column of A have a common factor 2 or lambda, then this factor may be removed and the value of the determinant is given by the product of the remaining determinant and lambda. Uh, like say for example, if you have your first row, let's just have your first row that's 2, 4, and 6. Then this is dot, 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 dot. And as you can see, the first row, all the elements of the first row have a common factor lambda, which is equal to 2, right? So you can remove that factor such that you just have 1, 2, and 3. Okay, and the value of the determinant is given by the product of the remaining determinant and lambda. So you find the determinant of this one and then you multiply with your lambda. So that's your determinant of your lambda a, which is equal to your lambda n a. Next, identical rows or columns. If any two rows or columns of A are identical or are multiples of one another, then it can be shown that the determinant of A is equal to 0. So if any two rows or columns are identical or are multiples of one another, like say for example, you have 1, 1, 1, and then dot, 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 and then your third row is 2, 2, 2. As you can see, if you're going to remove the determinant or the common factor for your third row, which is 2, then you have your first row and then your third column, which are identical. Then if you find for the determinant of this one, you'll see that the determinant is actually equal to 0. And lastly, adding a constant multiple of one row or column to another, the determinant of a matrix is unchanged in value by adding to the elements of one row and a fixed multiple of the elements of another column. So we still have the last property, which is the determinant of a product. If A and B are square matrices of the same order, the important thing here is that your A and B are square matrices of the same order. Then the determinant of A times B, this one here, is equal to the determinant of A times the determinant of B, or the determinant of BA. A simple extension of this property gives, for example, if you have vectors or matrices A, B up to G, then you can extend this one so that you have this expression here or this expression here, which are just all equal, and which shows that the determinant is invariant under permutations of the matrices in a multiple product.